So recall that yesterday we talked about opportunities in memory systems. Today I'm going to point out some broad solution directions. And this will be more like a blueprint for some of the solution directions that we're going to cover later on in the next few lectures. And then we're going to dive into Rowhammer. We're going to do a deep dive, as I mentioned yesterday, because it's such an exciting topic today. And it's something that's really unique in my opinion. And hopefully I will convey to you why it is unique. Some of you already may know, of course, and may have done the reading since your homework is out. Okay, so let's start. Basically, I'm going to, this should be a relatively short lecture for A, and then we're going to spend most of the time on Rowhammer. So basically, we're going to talk about solving the memory problem, and we're going to look at many different solution directions, at least in the initial part of the course. But later part of the course, we'll also cover some other solution directions like latency tolerance and prefetching. But so far, we've talked about a bunch of challenges, performance, energy, scaling, etc. Then the question is, of course, how do we solve all of these challenges? There are multiple directions, I think, especially going forward. One is, these are the directions we're going to talk about, actually. One is basically trying to fix the problem somehow. And I believe this requires some different thinking, which is really making memory and controllers more intelligent. And that's kind of the direction that the industry is moving into. Maybe a little bit later than academic research, as you can see today. And we're going to talk about both academic research as well as industry, what the industry is doing in this area. So this requires, I think, some new interfaces to memory, new functions implemented in memory, and new memory architectures. I call this actual system memory co-design. And one of your required readings is the main memory scaling paper that some of you may have read. It's assigned in homework 1. It's assigned as the only required reading. There are 5 other readings that are suggested, but you can pick 3 readings from those suggested readings. You don't have to do all of them, basically. But if you do more, of course, it'll be better. But that paper that we have written covers the system memory co-design nicely, so it goes along well with what we're going to discuss. And we're going to talk about these new interfaces, new functions, new architectures as we go along. I'm going to give you some examples right now also. But let me talk about the high-level directions. Basically, one is trying to fix it with existing memory technologies, let's say. And I think that's a very good direction by making the technology more intelligent, more capable, more flexible, more functional, hopefully better scaled that way. The second is somehow we want to eliminate the problems that we have, right? This, I mean, this may not be true, possible with all of the problems, but maybe there are some technologies that are out there that can minimize these problems, not necessarily eliminate them. So I think of these as investing in new technologies. For example, phase change memory was one example in 2000s until it was actually put into the market today. Of course, you still need to improve it, right? Even though it's in the market doesn't mean that it's in the best shape. So basically, that's something we're going to talk about. Can we replace, or maybe replace is a strong word, but more likely augment existing technologies with a different technology? And I give DRAM as an example because clearly main memory is dominated by DRAM today in pretty much all types of computers. But you could also think of replacing some other technology like flash in the storage side, right? If you're having storage scalability problems with flash, maybe you think about replacing it with maybe phase change memory or something else. So basically, that's the thinking. Or SRAM, that's also another example, right? If on chip you're having a bunch of problems, scaling problems with SRAM, maybe you try to replace it with some other technology. So the solution is applicable, solution direction is applicable at different levels. But I think we're going to focus a lot on DRAM since you were here in the last lecture, you know the importance of it today. Okay, so let's talk about basically what does this mean? Okay, my computer froze. Okay, this basically means we want to enable some new technologies. And I think once you enable new technologies, you also enable some system-wide rethinking of what happens to that technology. Where does that technology fit? And how does memory and storage change at different levels with some new technology? And I think with emerging memory technologies like phase change memory, these questions are very valid. How do we actually place phase change memory in the memory hierarchy, let's say? Does it replace DRAM? Does it replace flash? Or maybe it's a combination of both. How does it get exposed to software? Does it get exposed to software? How does it get exposed to the architecture? How does the microarchitecture deal with it? So basically, it requires a system-wide rethinking to enable a disruptive technology. And I think a lot of the technologies we're going to examine are really disruptive technologies that can change the future. Okay, so this is another direction. For example, if DRAM has a big refresh problem and Rowhammer problem, why not design or find a technology that doesn't have those problems? Right? Now, it's not going to be easy to find technology that doesn't have those problems, but also doesn't have some other problems, right? So it's good to keep that in mind. That's where we ended the last lecture almost. We talked about hybrid memory systems. We're going to talk a little bit more about that in a little bit. And the third direction also is interesting, I think, which is maybe we embrace the problem, right? Embracing the problem means that, okay, you have all these different technologies. None of them is perfect. And we embrace them all. We put them all or a subset into the system. And we realize that none of them are perfect, but map data intelligently across them. So here we're basically transforming the problem into some sort of programming or software problem where somebody indicates where data should be placed, or at least hints at where data should be placed and how it should be used. This way, maybe you can scale memory in a much better way, because now you're not relying on any single technology being really, really good. You're basically trying to make the best of multiple different technologies. For example, if DRAM has this retention time problem, and if you keep getting errors, maybe some part of your memory is much more reliable DRAM or some other much more reliable technology, and you map your reliable data or data that requires security guarantees to that really, really reliable, robust DRAM. So this is one very simple idea that we're going to briefly discuss in a little bit, and we may go into more detail later on. So I think these are three major solution directions. There may be other solution directions, and that's a good topic for discussion perhaps on Piazza. But we're going to cover these three directions in some detail. And I think if you may imagine other directions, as I said, but I believe if you look at all of these solution directions, they require some sort of cooperation between the software, hardware, and the devices. And we will see that as we go along, as we look into directions. Of course, some of the solutions that are developed will be more like point solutions, like can we solve the memory latency problem by better DRAM microarchitecture, right? And that's a good solution direction to examine. But not all of the solutions will fit that. Actually, most of the solutions will require this across the stack view that we talked about quite a bit in the last three lectures, which is really crossing from algorithms to even devices or at the very bottom. Okay, so let's go into a little bit more detail in these directions. This is again going to be an overview, and then we're going to actually put a blueprint for the next few lectures at the end of this lecture, actually. Okay, so what does new memory architectures mean? Basically, since existing architectures seem to have scalability and energy and performance problems, maybe we should look at a more memory-centric system design. In the existing system, memory is really not the center of the system design, right? It's really the processor that's at the center. But as you remember from the last lecture, memory controller is really at the heart of the system, right? Everything else, everything in the system, all of the computational units, plus all of the memory units and some storage units all go through the memory controller. Even the network unit today goes through the memory controller. If you look at some Intel architectures, network packets come and they go through, actually there's a direct cache access. They go through caches also sometimes, but they go through the memory controller as well. So in a sense, memory control is really the center in existing systems, except the system is not designed in a way that recognizes that memory is really at the center of the system. Basically, the system is still processor centric, even though everything really goes through the memory. So that's the key realization here. Maybe we should really be making the systems more memory centric, and we're going to talk a lot about that. And this leads to new memory architectures, new interfaces, new functions in memory. Can we actually do computation in memory, for example? Can we design memory to be much more lower latency than it has been designed with? In the last lecture, we talked about latency not improving much over time. And if you actually think about memory being the center of the world, maybe that's a really bad design choice to make, because you don't want to if something is the center of the world, you don't want high latency to that thing, right? So all of this falls down from a memory-centric system design. Basically, you want essentially better memory, better interfaces, better functions, better architectures. And on top of this, I think we need better waste management, because if memory is really important, we should really not waste it as well, right? As I mentioned yesterday, more than 30% of stuff, as I mentioned at some point, basically a good chunk of memory is zeros. So does it really make sense to have an expensive resource only to store zeros in it, right? Can we more efficiently utilize it? Or if we can access memory much faster, can we actually access memory much faster with simple changes to memory? Basically, efficiently utilizing the latency, bandwidth, and capacity of memory is really going to be important going into the future because it's a valuable resource. We don't want to waste any of it. And memory bandwidth is another example of this, actually. Okay, so there are a lot of issues to tackle here, clearly. What do we want to solve? We're going to talk a lot about reliability and security to begin with, and we want to enable this at low cost because this leads to high capacity without reliability problems. And this is important, and we're going to talk about that, especially starting with this lecture. But we don't. There are many metrics clearly in the design of memory, in the design of a system also. And memory is, assuming memory is a big component of the system, memory is actually going to see all of these metrics imposed upon it, right? Reducing energy is clearly important. Reducing latency is important. By the way, the first two, enabling reliability and reducing energy, sometimes are at odds with each other, right? For example, refresh, what we discussed, is a very simple example of this. If you want to get rid of refresh, well, if you want to get rid of retention failures in DRAM, you want to refresh more. That improves your reliability, clearly, but that increases your energy cost. So these two things are at odds with each other, as you can see. That's true for error correcting codes also, right? If you get errors in memory for whatever reason, retention could be one reason, something else could be another reason. You can add error correcting codes to your memory, but those error correcting codes now cost energy to you. They also cost latency as well, right? So reducing latency is also important since we're latency bound in many applications, improving bandwidth. So we're going to talk about all of these. And reducing waste actually is really important, I think, because there's a lot of waste in terms of capacity, as I just mentioned. A lot of memory is storing things that you may not even be touching, like allocated, or even if it's allocated, maybe all zeros or something that's repeated values. So compression could be a good approach. And some existing systems actually employ memory compression. IBM Power 8 is one example of this. And there are actual papers that are written. There's a lot of bandwidth waste. We will discuss this bandwidth waste. If memory bandwidth is very valuable, we don't want to waste any of it. For example, if we're not using a great chunk of our cache block, 64-byte cache block, maybe we shouldn't be transferring cache blocks in memory, right? Internally in memory, we've also discussed that there's a row buffer, right? That row buffer is, let's say, 8 kilobytes. If we're not using a good chunk of the row buffer, why are we transferring those 8 kilobytes into the row buffer? Maybe we should be doing something more intelligent, right? Because that's really wasting a lot of energy. And it's also potentially wasting performance, right? Because you're really transferring 8 kilobytes of data, and maybe only 8 bytes of that is useful from the row buffer. And this happens in a lot of applications. If you're doing, let's say, graph traversal, and if you have a lot of random accesses, because you're basically visiting nodes that are connected to each other in some random locations in space in memory, then essentially you're exercising this bandwidth bottleneck that I just talked about, both at the processor memory interface as well as inside the memory chip itself. So you're basically transferring 8 kilobytes into the row buffer just to access 8 bytes. And then you're going to get a row conflict, and you're going to open another row, access 8 bytes, and then access 8 bytes from the 8 kilobyte row. And then you keep doing this. So it's a huge waste in terms of both energy and performance. If you could somehow pack a large number of 8 bytes that you're going to really actually access into 8 kilobyte rows, and also into the cache lines that are going to be transferred into the processor, maybe that'd be a much better design in terms of reducing waste. So this is actually something important to realize, and we're going to talk a little bit about this going forward. So that's one approach, packing. The other approach could be compression, right? Basically, you compress data that you're not going to use, or you compress data based on its characteristics such that you work on compressed data. And there's also waste and latency, as we will discuss. Today, we're accessing memory with some number of nanoseconds, let's say 55 nanoseconds. But the question is that really needed for all of memory, under all conditions, and for all data? So it's good to ask these questions, basically. All of these innovations come from asking questions. We're accessing memory with 55 nanoseconds, let's say, row cycling latency. Is it really needed? Can I access faster at, of course, while being reliable, let's say, can I access faster at low temperatures, for example? Because at high temperatures, maybe the cells are leaking data very quickly and things are not working as robustly. So I need to give it more time to access memory reliably. But at low temperatures, I don't need to access memory at the same latency that I require to access memory at high temperatures. So this is another realization that there's a lot of waste in terms of latency, and we're going to talk about that also. So, and on top of that, I think enabling computation close to data gets rid of a lot of the data movement bottleneck that we discussed earlier. Remember that I talked about a paper that we wrote with Google that showed that more than 60% of the entire system energy is spent on data movement. And if you actually enable computation close to data, then you get rid of that data movement. And as a result, you actually enable a lot of these key issues to be tackled much more easily, because you're reducing energy directly, you're reducing latency, you're hopefully improving bandwidth because you're not transferring a lot of data on the memory bus. You're reducing waste on the memory bus. And if you actually enable computation close to data, maybe you actually enable reliability functions and security functions close to data as well. And that could make your reliability and security much more easier to deal with, as we will discuss in the next lecture about Rowhammer. So I spent a lot of time on these because these are really important, I think. And I believe these are really the key issues to tackle in any type of memory, frankly. We're going to focus a lot on the main memory initially, but again, keep your mind open. Clearly, we cannot cover a lot of things in detail, but a lot of these issues exist in SRAM also, but the trade-offs change a little bit. For example, SRAM also has a lot of capacity waste. It also has a lot of bandwidth waste on chip SRAM. It also has a lot of latency waste, but maybe not as badly as what we're doing with DRAM today. Latency is less of a problem, for example, in SRAM, because you're very close to the processing units. You're not going off chip. Energy is also less of a problem because, again, you're not exercising these huge interconnects that exist between the processor chip and the memory chip. Right? But trade-offs still exist at the same level. You still want to improve these things, but the benefit you get from improving those things on chip is much less today, because fundamentally it's on chip and everything is smaller, let's say, to deal with. Okay, but enabling computation inside SRAM is very, very interesting today because chips are getting larger and you have a processor and SRAM is distributed in a chip. And the question is, does it really make sense to move the data from a far away SRAM block on the chip into the processor so that you can operate on it? Why doesn't the processor send a message to the SRAM block saying, SRAM block, please update this data like this and don't bother me with it? Okay, so enabling computation close to data actually cuts across all memory technologies in the end. Okay, so this is solution one, basically new memory architectures. How do you design new memory architectures that are fundamentally better with memory-centric system design? And we're going to talk a lot about that. And we're going to cover a bunch of papers. Clearly, we're not going to cover all of the papers that have been published on this topic. And unfortunately, there are no textbooks that cover this information really well. That's why I'm going to give you papers and book chapters. Okay, and these are some of the papers that, okay, this is not working for some of the papers that we've been writing in this area. Actually, you saw the first paper, which is the radar paper over here. We're going to cover some of the other ones over here also, just to give you examples of what's going on in research. Okay, the second solution direction is somehow eliminating or minimizing the problem. Can we come up with some emerging memory technologies that are fundamentally better and that solve some of the problems? And some emerging technologies are actually very scalable compared to DRAM. Some resistor memory technologies, because they rely on resistance. We're going to talk more about that. I'm not going to go into a lot of detail. And they happen to be non-volatile also, which is a plus because DRAM is clearly not non-volatile. When you plug off the power, it loses data. Whereas if you don't have that problem, now you can build persistent data structures on top of non-volatile memories that are similar to DRAM. And they're scalable because basically like you can reduce the feature size to much smaller dimensions than DRAM, because you can reduce the current pulses, for example, in phase change memory. One example is phase change memory. Basically here you have some special material. It could be chalcogenide glass, for example, and you basically store data by changing the phase of the material. Material can exist in multiple phases, and phase change memory is 2 phases, amorphous and crystalline. And you basically heat up the material to change its phase. And different phases denote different encodings of data. And you read the data by detecting the material's resistance. And different phases have actually very different resistances. That's why you can actually read this reliably. So this is very interesting. And in fact, it was expected to scale to 9 nanometers when ITRS wrote its report saying that DRAM is difficult to scale to 35 nanometers in terms of feature size. So you can see that. But today, actually, I think the expectation has been revised to about 2 nanometers or so, maybe 3 nanometers. So it's actually very small in terms of expected scaling feature size. And as early as 2008, it was prototyped at 20 nanometers, which was much earlier than DRAM got to 20 nanometers. DRAM got to 20 nanometers like just a couple of years ago, a few years ago, basically. And this is a beautiful paper at IBM Journal of Research and Development that talks about the device characteristics and technology as of 2008. So it's a bit dated right now, but the fundamental characteristics of the device has not changed. It's phase change memory and it operates based on phase change principles. In fact, how many people use rewritable CDs at this point? I'm afraid I'll get the answer 0, although that's a difficult answer to verify. Does anybody use rewritable CDs? Nobody says yes. Interesting. I guess that's not surprising because, yeah, not really, I said. Oh, I got a +1. Maybe one person used rewritable CDs. That's good. It's actually not a bad medium, but rewritable CDs, for example, use some variant of phase change memory. Except, and it's very similar in terms of how phase change memory operates. Basically, you have 2 phases. And these 2 phases, rewritable CDs take advantage of the fact that these 2 different phases actually have 2 very different optical reflexivities. So in addition to these 2 different phases having different resistances, they have very different reaction to when light is shined on them, basically. As a result, you have an optical reading procedure, and that's well fit for CDs. And CDs take advantage of phase change memory to pack a lot of data into them, basically. So this technology already exists, except clearly you can imagine that this sort of reading process is a very slow reading process. More recently, people have focused on enabling a read device for phase change memory that's much more compatible with existing memory technologies, sense amplifiers, basically. And that they were very successful. And as a result, we have phase change memory in the field today. Okay, so I spent more time, but it's good to, I think, understand that these things exist. So other examples of emerging memory technologies are MRAM, magnetic memory, spin transfer torque MRAM. We're going to talk about that, and resistive memory and memristors. You may have actually heard about that. And there's some other memory technologies like racetrack memory that are maybe out there, or maybe they cannot make it in the near future. We'll see. We may see some of them also. The problem is it's not easy to replace an existing memory technology like DRAM with these other emerging memory technologies because, well, there are multiple reasons, clearly. One is manufacturing related, which we're not going to talk about now, but clearly manufacturing these emerging memory technologies is problematic. It requires a lot of effort. Somebody needs to do that effort to enable them. But they also have some, from the architectural perspective, they have shortcomings as well. For example, phase change memory has an endurance problem. If you keep writing to memory, at some point you cannot write to a cell because you've written too much. Because contacts degrade because of very high temperature writes. As a result, you have a problem called wear out or endurance. It's also called, you have limited endurance. So memory cells wear out. That's true for flash memory also. The flash memory wears out as well. Phase change memory wears out at higher number of writes, but the number of writes, let's say 10 to the 8 or 10 to the 9, is still not enough to immediately replace DRAM. And we will talk about that. So that's a big shortcoming, clearly, right? If a memory wears out when you write to it, you don't want to expose that memory to a lot of writes. Whereas DRAM is exposed to a lot of writes from the processor. Imagine that, right? So it's difficult to replace this sort of memory. And there are also latency, energy, etc., other issues depending on the type of memory. And we're going to talk about that. And then the key is basically understanding that these issues can be solved, again, with an architectural approach. Okay, solved may be a very strong word, but maybe mitigated, right? Maybe you can mitigate these problems by designing across the stack again. Okay, we're going to talk about that. But this solution direction is also very much cross-layer solution direction. Okay, so we've been working on this also. So I'm going to pick and choose some of our papers and some of other papers in the field to talk about this as well. So it's an exciting direction, as you can see. Otherwise, I wouldn't be working on it as a researcher, right? If I'm not excited about something, why would I be working on it? There's very limited time in life anyway. Okay, So I think we're going to also talk about this basically because it's going to be hopefully clear that no memory technology is good enough in every single metric, as I mentioned last time. So we're going to talk about this solution direction going forward, which is already happening at a small scale, but I believe this heterogeneity is going to increase into the future. Basically, the idea is to have hybrid memory systems with different characteristics put together, and you design the hardware and the software to manage data allocation and movement to achieve the greens as much as possible while avoiding the reds as much as possible of any technology. That sounds good, right? Of course, this complicates the system, but if you can do it well, again, it's a cross-layer solution. How do you actually do this? And I spent time yesterday on this, so I'm not going to spend more time right now until we get to the lecture where we talk about hybrid memory systems. But it's good to realize one thing over here, which is this heterogeneity is a very fundamental principle in architecture design. Whenever you want to scale, become more efficient, get the best of multiple worlds, the first thing maybe should come to your mind is heterogeneity. If you want to get the best of multiple worlds, put those multiple worlds into your world and try to design the system such that you get the best of them as much as possible while avoiding the negatives of each of them. So it's a very fundamental principle. I think humans are also very heterogeneous, and the way we deal with life is also very heterogeneous. So this is nothing new in a sense, in the broader sense. Why not put multiple technologies into memory? And this is already happening in CPUs. Like we have a lot of heterogeneity in this side of the system. I don't want to call it necessarily a CPU, but the computational part. We have a lot of accelerators, for example, and for the same reason, we want to get higher efficiency. We want to get the best of different worlds, because clearly a general purpose CPU is not good for a video application that's really commonly used. So we want a video accelerator, and we get better efficiency, better performance by offloading things that work well on the video accelerator to the video accelerator, and true for GPU also, for example. So the heterogeneity principle is actually now encompassing different parts of the system in addition to the computational parts, as you can see. Okay, so keep that in mind. A lot of the things that you will see are, I think, fundamental principles, and I'll try to point that out as much as possible, but sometimes I may miss them because it's so obvious to me at this point. Okay, so we're going to talk about clearly both of them plus combination of them. So let me give you one example of this because I like this example quite a bit, and this example actually is really cross-stack example. So basically, if you look at applications, not all data, and we've talked about errors in the past lecture. We're going to talk more about that. But let's assume that you have some bit flips in memory. It could be random bit flips. It could be induced because you reduce the refresh rate. It could be for whatever reason. But let's assume that you get these bit flips. And if you inject these bit flips, how bad is it from an application's perspective? Meaning, what is the memory error vulnerability of different types of data in a given application? So this type of data, for example, has high vulnerability. What does that mean? If you get a bit flip in this particular data structure, the application crashes immediately. Why? This is really critical for progress. It could be, I don't know, something that's really important for the application. It could be a linked list traversal that really determines what happens afterwards, right? So it could be important. Whereas this other data, if you inject bit flips into that data, you don't get much problems. The application doesn't crash, certainly. And in the end, maybe just a pixel changes on the screen. And maybe no one recognizes that, right? So I gave you clearly an application that's tolerant. Or another application, it could change some input data into a machine learning classifier, let's say. But the machine learning classifier is robust to some bit flips in the input data because it's very statistical anyway to begin with. So it's a deep neural network, let's say, some input data, some of the bits flip, and in the end, you will get the same answer because the classifier is robust enough in its network. So this could also happen, right? And we're going to see an example of this when we talk about the Eden approach later on. But basically, there are different types of data that have different vulnerability to bit flips or errors, let's say. And there are also intermediate things that you can imagine also. Sometimes things crash, sometimes don't crash. And sometimes you get problems, sometimes you don't get problems. So you can imagine this being a spectrum of vulnerabilities. So clearly, these data have different properties from a high level reliability perspective. And today, what we're doing is we're treating everything the same. everything gets stored in DRAM, and everything is essentially equally exposed to faults. Now, the question is that a good design? Or the next question is that a scalable design? And I would argue that both of these answers should be no, because basically, why is it not a good design? Because we're not intelligent enough in handling our data. We don't care about the vulnerability of different data. We just store it into a single type of memory and hope that everything is good. Or we impose too strong requirements out of that memory such that the memory should be really reliable, thinking of the worst case. But maybe that's not a good approach, right? If you're intelligent, you could actually make things much more scalable and much more efficient by actually communicating information about the vulnerability of different data. And also, it's not scalable necessarily, because if you actually impose a strong reliability requirement from all of your memory, let's say DRAM, then you run into the issues we talked about in the previous lecture, right? Then all of your memory needs to be completely reliable. And this becomes maybe not so easy to sustain, as you also want high capacity, low latency, low energy, high bandwidth, etc. Right? So basically, you cannot get everything at the same time, perhaps. And the realization that I show you in this picture, which I think is really important, if you can somehow distinguish between the vulnerability characteristics of your data, maybe you make your system more scalable and say some of your memory should be reliable, yes, because some of your data requires that sort of reliability. But some of your memory, or maybe a good chunk of your memory, doesn't need to be reliable. Of course, this depends on the application. This depends on what is the vulnerability. I didn't give you a measure. For example, what kind of error rate can this application's data structure tolerate without causing problems to the user, let's say, and understanding that. So you need to do the hard work to figure that out. But once you figure that out, you can design a much more scalable memory system. And that's the idea over here. And that becomes a hybrid memory system like in the previous picture. Somebody identifies vulnerability of data. Let's assume that it's black and white right now. It's vulnerable and tolerant. I don't believe it's black and white. It's really a continuum, I think. And it's really not just about vulnerable or tolerant, but it's really about what is the error rate that you can tolerate. In fact, even DRAM has an error rate that you can tolerate, except it's very, very low today. We can tolerate soft errors, for example. Sometimes your computer may reboot itself because a soft error might have happened. Now, it's okay if it happens once in a blue moon. It's not okay if it happens every single minute. Then we would have no possibility of having this conversation or having this lecture over Zoom at this point, right? So basically, every memory has essentially an error rate that it promises. Now we want to match, we also want to figure out an error rate that can be tolerated by every piece of data and match it to underlying memories. That's the idea, basically. Assume that we've figured out the error rates that different data can tolerate. In this case, it's black and white, can tolerate, cannot tolerate. And then we design different types of memories that essentially are commensurate with those error rates. And that's the idea over here. This is called heterogeneous reliability memory. Your vulnerable data goes to reliable memory, and your tolerant data goes to low-cost memory, hopefully less reliable memory. And we published this in DSN 6 years ago. And then question, of course, there are many questions clearly. What is this reliable memory? How do you design it? It could be ECC protected, for example, error corrected code protected. It could be very well-tested chips. But this low-cost memory can be, maybe you want some detection of errors so that you can actually satisfy some error rate, fine. But you can now have less tested chips. Remember, testing cost is actually a good chunk of memory design. Actually, it's a good chunk of processor design today. If you look at how long it takes or how much money it costs to design a processor, more than 50% of the cost is really in verification and validation today, both in terms of time and money. It's a bit sad because you really need to verify, validate, fix the errors, and do another run, production run. And then if needed, do it again today. And that's true for memory as well. Basically, a good chunk of the cost of memory is really about testing today. But the fact that you know the characteristics of your data enables you to test your memory less. Now your memory becomes cheaper, and also maybe your memory becomes scalable. And maybe a lot of your data is tolerant today if you're feeding a machine learning application with that data because the machine learning application may have good tolerance to it. And we're going to get back to this in the specialized case of machine learning, because if your application is already tolerant to noise, because it's very statistical to begin with, this sort of trick is much easier to do. Video is another example. Audio could be another example. So these applications where you're interacting with the user, but the user really doesn't notice some faults that are happening on the screen or in the sound or etc., are good applications where you can actually play these tricks. Okay, but all applications have some different types of vulnerability or different sorts of vulnerability in their data. Okay, so basically what we did in this work was we actually collaborated with Microsoft and looked at how we can partition their workloads such that we can do exactly what I show in this picture. Annotate data as vulnerable and tolerant. And my student Yishin, who did his PhD thesis on essentially memory reliability, flash memory reliability, did this on his essentially manually by inspecting the different data. And it basically, he partitioned the data into vulnerable and tolerant, and then basically mapped it to different types of memories, ECC protected and low cost, as you can see. And if you actually do this, what you can do in a data center is you can get rid of a lot of ECC that is kind of over provisioned. If you've got the systems, you don't always need ECC if most of your data is tolerant. And we show that you can actually reduce hardware costs significantly, get rid of ECC while reaching a good availability target. Okay, you can read the paper more, but let me go into a little bit more detail, because this is actually, there are multiple principles here. One is heterogeneity, and the other is really cutting across the stack, because you cannot do this just at the microarchitecture level, because microarchitecture level has no idea as to the reliability of the data, right? So somebody needs to annotate your data in terms of its vulnerability characteristics. Somebody needs to do this characterization, and there's a spectrum over here, vulnerable to tolerant. And this needs to get communicated to the underlying system software. And the underlying system software needs to map application data to the heterogeneous reliability memory system with some solutions. I'm not going to go into the details over here. And then underlying hardware needs to support it. The hardware needs to have a heterogeneous reliability system, as you can imagine over here. And there is a huge design space just in the hardware itself, but also a huge design space in terms of how you would determine it, how you would communicate it, and how you would do the mapping in the system software. So this is a really truly cross-layer approach, as you can see over here. It's also a data-aware approach. We're going to talk about data-aware architectures. So today's systems are not very data-aware. So if you look at a general purpose system today, you really know very little about the characteristics of the data that you're dealing with at the system software level, as well as at the architecture level. So if you look at architecture, you have no idea what the vulnerability of the data is. You usually have no idea what the security characteristics would be, no idea about the characteristics in terms of compressibility of data, for example. So this is really arguing for, we need to know more about the data. And if we do it, we can design a much better system. Okay, I call this data-aware architectures. So very quickly, basically, if you actually do what I just suggested, you can get a system that's quite good, actually. You see a chart over here. In this case, we have five different metrics to evaluate the system with. And Ultra is better in all of the metrics, as you can see. And we're evaluating a typical server, consumer PC, our heterogeneous reliability memory system, and just less tested DRAM chips, and heterogeneous reliability memory system with less tested DRAM chips over here. And you can see that bigger area means better trade-off over here. And this HRML system has a better trade-off compared to everything else. It's not the best in all metrics. Clearly, this is better over here in terms of cost savings, but it's not very good in terms of single server availability over here. So again, you want to satisfy everything over here, and you're not going to be able to satisfy everything in the best way, but you can get close. Okay, with a heterogeneous system. Okay, I don't know what happened. Yeah. Okay, so basically, I've spent a lot of time on this because it's important and it's a good area, but this is a paper that we may assign at some point, but you can take a look at it. And there's a lot of research that could potentially build on it going into the future. And HRM, this heterogeneous reliability memory, is an example of our axiom. If it weren't clear before, I think this picture could make it clear, because someone needs to specify the characteristics of data. And this could be done algorithmically. It could be done in the language level. I think it's very hard to discover in the system software level, but maybe there's a way, I don't know. So it needs to really be done at the higher levels of the stack, because it's really a semantic property of the data that's dictated by the user, right? And that needs to get communicated all the way into the devices over here. Well, microarchitecture for sure, but maybe the devices need to be designed in a manner that's aware of potentially different characteristics of the data that can be communicated from the top. So it's really about top meeting the bottom in a really good way. And I really like this approach because I believe this is really a good approach for scalability of memory going into the future. And I'm going to give you other examples later on in the future lectures. Okay, any questions? Okay, so let's move on. Again, we can always discuss this on Piazza. Okay, so the orthogonal issue we also talked about is memory interference. This is another example, I think, of a cross-stack approach, although the problem can be tackled in different layers as well. But I think in the end, you need to communicate between the layers in some way. And the best approach is probably an approach that fundamentally communicates between different layers. And the problem, as you know, is memory interference between cores is uncontrolled. And this leads to a lot of issues like unfairness, starvation, low performance. And as a result, you have an uncontrollable, unpredictable, and vulnerable system, as we've seen with the memory performance attacks paper, right? And the solution here is quality of service-aware memory systems. And this is, again, better memory architectures, right? It's not, this really cuts across whether you design a better fixing the memory problem or enabling a new architecture or embracing the memory problem, like we've done kind of in this heterogeneous reliability memory is also embraces the memory problem. But this orthogonal issue really cuts across the stack, basically. Regardless of however you fix the memory problem, you're going to have to deal with memory interference somehow. And that requires, I think, a quality of service of our memory system. In this case, we want to design the hardware to provide some configurable fairness substrates with different kinds of techniques, scheduling, partitioning, throttling. We're going to see all of them. And the software needs to be designed to configure this configurable substrate, which is hardware, through a good interface, hopefully, to satisfy different quality of service goals. And that's the idea of here. It's very hardware software cooperative again. And I believe this sort of memory system can provide predictable performance and higher efficiency. And we're going to see example of this. And I think one of the things that's really going to be important going into the future is strong memory service guarantees. How do we solve this problem of providing strong service guarantees? And the idea is to satisfy performance and service level agreement requirements in the presence of a lot of messy, shared, heterogeneous resources, heterogeneous agents, heterogeneous memory and storage, and different kinds of heterogeneous hierarchical memory levels. And I think one approach that we have been following, and that's important to follow, I think, is to understand how we can model the system. Basically develop techniques and models to accurately estimate basically how well you're doing in terms of your performance requirements for a given application or agent in the presence of resource sharing. So it's a performance model. You estimate the performance loss or relative progress in terms of how well you should be doing. And once you get that estimate through some model for every single application and agent in the system, of course, reasonably accurately, now you also need mechanisms to enable resource partitioning and prioritization at all of these resources that we've discussed, such that you can basically enable the applications to achieve their required performance levels. So how can you do this? For example, if you know how an application is doing, it's not satisfying its performance requirements, but some other application is well ahead of its performance requirements, maybe you trade off some resources between them, right? But this requires some configurable hardware substrate such that you can do it. So this is very important, I think. Again, this is a very hardware software cooperative approach. And on top of this, of course, as we've discussed at some point, you want to have high system performance. You don't want to give up high system performance and efficiency. And that makes the problem difficult. If this was not the goal, then quality of service or strong memory service guarantees is really easy problem. Just run one application alone in the system and provision your system such that you can get the latency and bandwidth requirements or whatever requirements you need from the system for that application. That's a terrible approach in terms of efficiency, clearly, right? You're running one application on the system, which is capable of running many, many applications, as we discussed with consolidation, right? Okay, so this is a very good direction going into the future, and we're going to talk about that also in the later lectures, and these are some example papers if you're interested in looking at that right now. And I'm going to actually cover some example papers in the next few slides also. So we're going to also talk about memory controls a lot. This is something, again, very close to my heart. In fact, let me give you very quickly my personal story before we end this lecture. Basically, I started looking into memory controllers when I was an intern at Intel. And this is, I'm proud of this patent that we filed with my internship mentor, Eric Sprengel. What we did in my first internship at Intel is actually look at how we can schedule requests in a memory controller to prioritize between different prefetches and memory accesses. And that's the idea over here. There's an idea, we basically wanted to, if prefetches are accurate but late, maybe you should be really prioritizing them. So this is really the core of the idea. There are other prioritization mechanisms in the patent. You don't need to think about that. But the core idea is really some prefetches, we know that they're good, but they're late. If the memory controller doesn't prioritize them, they'll be even later, essentially they'll be useless. But if the memory controller prioritizes them, even ahead of some demand requests, that's the interesting part, even ahead of some demand requests, you get better performance because this prefetch will in the future lead to a demand request to be eliminated. That's the idea. And this is one of the earliest works that I've done on memory controllers. Later, we did a lot of work on memory controllers. I'm going to actually briefly flash them to you. But it's good to think about the problems that you're working on initially, I think. And I enjoyed working on this. At that time, actually, it was not a traditional memory controller. At that time, in 2000s, even earlier also, the memory controller was off chip, actually. So what you did have in the processor was a front-side bus controller. It used to be called front-side bus. Terrible name, I think. But it's essentially a bus that connects the processor chip to the memory controller chip. Now, a memory controller has its own buffer. And it does its own reordering inside. But because it's on a separate chip, it has no idea what's a prefetch, what's a demand, ... And at that time, the algorithms that were used in the memory controller were actually very simple. So actually, at that time, the memory controller algorithms were first come, first serve. First come, first serve is no scheduling, basically. You don't do any scheduling at the memory controller. You basically have a queue. It's a first in, first out queue, right? That's it. That's what a queue means, basically. It's first in, first out data structure, which means that you're not doing any scheduling on it. Later, actually, some memory controllers added row hit first scheduling, and that was after Pentium 4, I think, at Intel. Which is good because now you're actually exploiting row hit first requests. That's good. Remember, the patent that provided row hit first was in 1997, so it's as late as 1997 at that time. So basically, what we wanted to do is to shape the access stream, access schedule that goes into the memory controller chip at the front side buffer, bus buffer. So we did scheduling aggressively at the front side bus controller, such that the memory controller gets a good stream that would actually do what we want. Meaning that sometimes we prioritize prefetches over demands. Otherwise, there's no way you could do that because the memory controller has no idea what's a prefetch and what's a demand. That's the idea, basically. So I'm proud of it, and I just want to give you some historical perspective because I think it's really important for people to see how other people do research. And this is something that I never published. You will see other stuff that we have published also, but clearly it was published as a patent over here. Okay, so you see that later this sort of work actually inspired us to look into memory controllers even more carefully after I finished my PhD. And that was my first project after I finished my PhD, basically. Basically, I always believed that memory controllers are extremely important. And at the time I finished my PhD, memory controllers actually became integrated on chip because that's what we argued for actually at that point in time as well, as early as 2000. Now, interesting thing is, Intel was resistant to actually put the memory controller on chip for some reasons that I could never understand. And while I was an intern, I was always asking why actually, why not put the memory controller on chip? And there are reasons for it, I think. If you have a separate chip, you can make more money potentially, but it's terrible for latency actually. If you want to reduce the memory latency, if your memory controller is on a separate chip, now you go from the processor chip to the memory controller chip first, which adds your latency, and then you go from the memory controller chip to memory schedule requests. So this adds latency to the entire memory access, which is terrible. And you have integration capability to put the memory controller on chip and get rid of this memory controller chip, basically. And that's essentially what AMD did. And after AMD did it, Intel had to do it also because AMD showed you could actually cut 1/3 of the memory access latency by getting rid of this really truly unnecessary memory controller chip from the system. But of course, there are other benefits. We will discuss this also. If you have a separate memory controller chip, now you can actually plug out that chip and plug in some other chip, right? Basically, you can enable a processor chip to work with many different types of memory, potentially. Whereas if you bake in your memory controller into your processor chip, now you're working with a single type of memory, or with n types of memory where you designed your memory controller for those types, right? But of course, today, there's only one type of memory a processor chip can work with. So you design it for one, because it's hard to do that, because you actually need to go through the physical layer. You need to design the physical layer to actually communicate with the chip. So there's a benefit to not integrating the memory controller on chip for both scalability and also plugging out and being compatible with different types of memory technologies. There's also scalability benefits, because now you can actually expand those chips and have many different memory controller chips. So you can actually increase your memory capacity by having different, many of these buffer chips that you can communicate with. And this is actually an approach that's used by IBM in their power systems. They basically communicate with additional memory controller chips. And this is very scalable now, because there are many potential memory controller chips, and they essentially can have a huge number of memories, a huge amount of memory in their system. Now, of course, this comes at the cost of latency, as I said. Your latency is not as simple as you go through your memory controller on chip and you access memory. You have to go through one more chip at least to go to memory. Okay, so basically, the historical perspective, AMD incorporated their memory controllers on chip. And after that, Intel had to do it in a sense. And essentially, the general purpose x86 controllers all got integrated onto chips. That's true for ARM today as well, for example. And later, we've already discussed memory performance attacks, but memory controller becomes a point of unfairness also, as you see. And we looked at a lot into memory controllers to solve that problem. This is one example. Our memory controllers actually parallelism or batch scheduling. We're going to talk about that later on, but this is just some foreshadowing, showing the importance of memory controllers. We uncovered that there's more to do in memory controllers. And this is actually a review that we got for Power BS from ISCA. Sometimes you get people appreciate these papers, as you can see. And this was actually a very strong accept from, I don't know who it is because it's anonymous reviews, but this was a positive review that you can see. And variants of this Power BS was actually implemented in Samsung SoC memory controllers. And we're going to cover some of these other memory controllers as we will see later on. But basically, I want to point out this heterogeneous systems part. It's important to see that memory controllers are becoming much more complicated today also to deal with heterogeneity. And in this case, we're dealing with heterogeneity on the processor chip. Basically, we have a lot of heterogeneous agents, CPUs, GPUs, hardware accelerators, and some of them have deadlines, some of them don't have deadlines. How do you satisfy all of that with a memory controller? And this is one work. I believe this is the state of the art in this area, but there may be some paper that I may have missed in the recent years, as you can see. And then predictable performance important, and we're going to talk about that later on. But basically, I think my point here is memory controllers are also critical to research, and they're really the gateway to accessing main memory. And they're going to be more important in the future. That's why it's good to think about a memory-centric perspective. And this is one of the reasons why they're going to be more important into the future. Everything is going through the memory controller, and whatever is going through the memory controller from the top over here is heterogeneous. And whatever the memory controller is controlling is heterogeneous. And maybe the memory controller needs more information, needs more intelligence to actually satisfy the requirements and do functions that are needed by different applications while controlling these heterogeneous memories. Basically, it needs help from the higher levels, including the software, to manage what's going on over here and to also satisfy the characteristics or requirements of these different applications, of which there are many, many that are running and that are going through the memory controller. Now, I don't even show the network and the storage over here. There's also network and storage that's attached to the memory controller, if you will. So basically, there are many goals, many constraints, and many metrics that you need to optimize, and it's a complex system. So this needs to be more intelligent going into the future. And I think we have one promising approach that we have looked into initially in 2008, in this ISCA 2008 paper, is designing memory controllers such that they can automatically decide policies on their own, as opposed to humans somehow trying to dictate policies that will be employed online. The memory controller automatically figures out what is the best policy to follow based on learning, machine learning from from interaction with its environment. Basically based on learning from its past actions. And reinforcement learning is something that I like a lot. It's a machine learning approach that's very, very different from deep neural networks. Also, although there are deep reinforcement learning networks today also, which are a combination of both. But basically here, the idea is you are a reinforcement learning agent as a human also. Basically, you take some actions. Your actions lead to some rewards in the short term or long term. And you keep track of what state you took the actions in. And then you associate these state action pairs with long-term reward values that you get from the environment. And then over time, you try on a given state, you try to pick the action that leads to the highest learned long-term reward value. So over time, basically, you learn to choose actions in a particular state that leads to the highest rewards. As humans, you could behave this way. Some things we do are actually very much related to this. For example, when you touch a stove, you don't do it again because you clearly get a negative reward from touching a hot stove. From touching a cold stove, you also learn that you get a neutral reward, let's say. Although maybe cold is good sometimes, so you get a positive reward depending on your state, right? Your state may be, I'm very hot, let me touch this cold stove, and I get colder. So in that case, actually, your action leads to a positive reward, given the state. So over time, you learn this basically as a human, and you learn this when you're a baby basically very quickly, and then you don't do it again, and it gets registered in your mind, and you don't lose it, hopefully. So basically, the idea is to get the memory controllers to the same state, and not many parts of, actually no parts of the system is like that today. But maybe there's a better way of designing systems with this sort of machine learning, such that the system is much more intelligent and data-driven, as opposed to humans dictating the decisions, which I believe is actually really impossible to do, because there is a huge state space, a large number of metrics, large number of actions that can be taken. And how is it possible for a human to actually decide offline? Human in this case could be the memory controller designer, but you could generalize it to an operating system scheduler designer also, for example. How is it possible for a human to decide a really good policy that's going to work well under all conditions, for all workloads, for all states, and for all different metrics at the same time? I think this is impossible for a human. That's why I believe this approach is a very, very promising approach to look into. It's not an easy approach to follow, because you need to know about architecture, you need to know about machine learning, and you also need to be a good architect, in my opinion, to figure out how to do this. But I believe there needs to be more done in this area, and it's a very promising research direction if people are interested in it. Okay, so basically, I think the future is not just memory, but memory controllers pose many new problems. So it's really exciting. And I think main memory needs intelligent controllers like what I described, but also even more intelligent controllers that can do computation as well, and that can basically learn from their actions, past actions, to enable both computation and better system design going into the future. So I finished my last lecture with this takeaway also, and I'm going to finish this lecture also with this takeaway. And we will see more examples of this intelligence. And again, to enable this sort of intelligence, we must take this expanded view of computer architecture. I've given you a lot of examples of this expanded view already. We're going to see more and more examples of this going into the future. So let me talk about what we will cover, at least in the next few memory lectures, let's say. And then we're going to take a break, and then I'm going to start with the rope hammer. So basically, we've already covered memory imperative and trends, and we've already given a lot of different examples of memory. We're going to talk about rope hammer. It's not clear if we will finish in the next hour, because I always seem to be taking longer than needed. But as long as it's interesting, if the anecdotes that I deliver are interesting, then I'd be happy to do it. I don't want this to be dry for you, since it's not easy actually to follow, I think, online. So hopefully anecdotes help. But feel free to ask questions also to interrupt me. And then we're going to spend maybe a couple of lectures on computation in memory and different approaches to it. And then we're going to talk about latency issues in memory. We're going to talk about data-driven and data-aware architectures. And then we're going to talk about memory controllers and quality of service. And I think in all of these, we're going to talk about guiding principles and research topics sprinkled around. but we may actually spend some time, a good chunk of a lecture talking about this as well. So again, this is a static schedule. Dynamically, it may change depending on what we think may be good to cover, depending on how the lecture flows, but it's not a bad static schedule to begin with because it's based on past year's dynamic schedule. So we're basically copying and pasting past year's dynamic schedule. Okay, so, and we're going to cover some papers, but I mentioned this paper earlier. I didn't assign this paper because this is the earliest paper that I have written as a position paper, but I did assign this book chapter, which essentially I view as maybe a book that goes along with what we're discussing. It's a little bit dated. It's 5 years ago, as you can see, but I think it's also shorter because it's a bit dated because it doesn't cover a lot of works that I'm going to cover. But it does cover the basic approaches and things that we're talking about, basically, in terms of the different challenges and solution directions and different examples. So hopefully you're doing this reading, and I would like you to review it also as a critical review. Okay, so basically, these are, I'm going to finish with these challenges in memory scheduling, memory scaling. We talked about a lot of these: data retention, reliability and vulnerabilities, latency and parallelism, energy and power, and memory's inability to do more than storing data. And we're going to cover all of this in the next few lectures. Clearly, we've covered data retention a lot. We may get back to it briefly, but I'm not sure. I think I've assigned enough readings. If you're interested, you can take a look. By the way, somebody asked the question of which readings should we prioritize. I think that's a good question. And if you can take a look at my answer on Piazza on it. Basically, prioritize the readings that are really required in your homework, and then prioritize things that we cover in lecture, and then prioritize things that look interesting to you. And sometimes in lectures, I say, okay, we don't cover some reading in detail, but I say, oh, this is really interesting. That may be something you may be interested in, so read. So nothing is really required except for what we assign in homework as required. But of course, it helps to do the readings that we cover in lecture, because that will emphasize the learning, hopefully. But you may also take a different approach, which is, okay, this reading we've covered in lecture a lot. So I learned a lot from it. So I'm going to skim through this paper, and I'm going to spend my time on reading another paper that is on the recommended list. That's another approach, of course. Again, this is an advanced course. We won't have a lot of readings except for the homeworks. As a result, you have a lot of freedom to choose. But I would that's the prioritization I would recommend. And you can read my post on Piazza on this. Okay, so basically we're going to look at memory scaling a little bit more from the perspective of reliability and security. And we're going to talk about Rophammer next. Okay, I took much longer than expected because I think I told you a lot of hopefully interesting stories. Hopefully they're not interesting only to me, but hopefully you can learn from it. Based on my experience, you can learn something from it also without living that experience clearly, because I don't think it's an experience that can be lived again, because the world is different now, right? You're not going to be back at a point where people are designing, in my opinion at least, people are designing chips that are separate memory controller chips. There are some that exist, as I said, for scalability reasons, but I don't think they're going to be as common as they used to be before. Okay, any questions? Is there a question? Okay, is there a paper that summarizes some of the approaches for better memory controllers? Okay, that's a very good question. I mean, this, I think I would recommend the paper that I have required. I'm not sure if that covers the question that you're asking. But I'm not sure if there is a single paper actually that covers all of the approaches that for better memory controllers. So why don't you read the main memory scaling paper, and if you still have a question on this, please feel free to raise it. Okay. Okay, so no other questions. Let's take a break. Let me see, where's my cell phone? So it's right now 2:11. Let's be back at 2:21, and we'll continue with Rophammer. So hopefully that'll be exciting.